Here we go. Sound check, sound check. I think I can hear myself. Yep. And next is a video check. Do I see motion on the screen? Yes, I do. Okay, we are good to go then. So, first off, sorry for being about 10 minutes late, but the good news is we don't have a very long one today. At least I hope it's not going to be very long, because that's what I said last time. And that didn't turn out to be the case. But yeah, today is going to be pretty easy compared to most of what we've been doing. Assuming, of course, that you have been, practicing and making sure that you understand the concepts well up to this point. If you were just kind of speed running through the course and just have a sort of superficial knowledge of everything, and you only care about acing the exam and not about truly understanding physics, then it might not be as easy for you. But without further ado, let's go ahead and discuss what we're doing today. So today we are going to do rotational kinematics. Rotational kinematics. We're just going to be introducing some really simple concepts involving rotation. Basically, they're going to be the rotational versions of displacement, velocity, and acceleration. And once we discuss those, we will also look at how they, what's the word I'm looking for? How they redefine our understanding of circular motion a little bit. We'll get an alternative equation for centripetal acceleration using one of our new variables. And what else? If you're looking in the course plan, you might see that after this topic, I'm supposed to have center of mass and moment of inertia. I'm not going in that order. I'm going to cover torque and static equilibrium involving basic torque first before I introduce that. So that was something that I wanted to mention just in case anybody was reading that and looking at the next stream that I have scheduled. So there's my explanation for that. I'm not neglecting it. I just feel that it's more appropriate for it to be introduced after introducing the concept of torque. Although maybe I'll reconsider. We'll see. But back to rotational kinematics. What was the other thing for today? I guess the other big thing with rotational kinematics is just paying attention to your units, because we're going to have 3 different units that are typical for your rotational quantities, and knowing how to convert back and forth between them is going to be important, especially for the later part of the chapter. If you've done pre-calculus trigonometry, the units that we're going to work with shouldn't surprise you too much. You will have dealt with them before. If you're an advanced algebra student who is just, studying AP physics while they're still in middle school, you might want to pay closer attention once we get to that part of today's lesson. And I think the rest of our time is just going to be spent doing a couple of really basic problems, and that'll be it. So before I talk about this, Do I want to do the simulation right now? Yeah, I guess I do. So let me just write down some of our new quantities that we're going to deal with. So some new physical quantities, some new rotational quantities that we want to deal with. One is going to be angular displacement. Angular displacement, or some people like to call it rotational displacement. Angular displacement. Why is it called angular displacement? Well, we represent it with the symbol delta theta. And it's basically the angle that something goes through when it rotates. We'll illustrate this in a minute when we open up the simulation. But basically, if you have, for example, a child on a merry-go-round, and the merry-go-round is spinning, and here's like the bird's eye view, we're looking at the child's head from above, and the merry-go-round is spinning like this. If it spins by, say at one moment in time, the child's head is here, and then at some other moment in time, the child's head is over here, then we would say the angular displacement is, what is that, like 85 degrees? So it's the amount of degrees that you rotate, but that's not the only unit of measurement we use for it. It can be measured in 3 different things. It can be measured in degrees, revolutions, which is just the word that we use for a full rotation, or radians, And those of you who've had pre-calculus and trigonometry are already familiar with the concept of radians. So let's go ahead and take a look at how to convert between these 3 before we define our other angular quantities. So degrees, that one is self-explanatory. If this thing rotated through 85 degrees, we all know what that means. That's intuitive to us. I don't think that needs explaining. Revolutions. So 1 revolution is a full 360-degree turn. So you can actually convert between degrees and revolutions, because you can say 1 revolution equals 360 degrees, and then you can just do dimensional analysis. You can do, if I have 85 degrees, then I can multiply it by 1 revolution over 360 degrees. This is multiplying by 1 because a revolution is equal to 360 degrees. So the degrees cancel out and you're left with revolutions. 85 3/60ths of a revolution is how much this thing was displaced rotationally or angularly. That is a hard word to say, angularly. 85 over 360, what is that going to be? 85 over 360 is about 0.2361. I think I'd rather just have it as a simplified fraction. 17 over 72. (17 over 72 of a revolution). Okay, and then what are radians? For those who haven't done pre-calc and trig, radians are just a way to define angles in terms of real numbers that don't depend on this number 360. 360 degrees is kind of an arbitrary choice. There is nothing inherent about circles that makes the number of degrees for a full circular turn 360. 360 is just one of those special numbers that the Babylonians thought was a good number to have because it has a lot of divisors. It's what's called in math, it's what's called a highly composite number. 360 degrees, or well, without the degree, just the number 360, is a highly composite number. Which just means there's a lot of numbers that it evenly divides by. It divides evenly by, of course, 1 and 2 and 3 and 4 and 5 and 6. The first point where you hit a snag is 7. 360 divided by 7, not very clean division there. But it divides nicely by 8 and 9 and 10, not so much by 11. It divides nicely by 12, and not by 13. Not by 14 either. It divides nicely by 15. So already you're seeing, just counting from 1 through 15, you're already seeing that there aren't that many gaps. A lot of numbers, most of the numbers we've listed off so far, 360 divides by. The Greeks preferred 5040 because, well, it can divide by everything 360 can divide by, and then some. But yeah, these are highly composite numbers, and there's a YouTube video where the author of the video calls these numbers anti-primes because they kind of do the opposite of prime numbers. Prime numbers are numbers that can only divide by themselves in 1, have as few possible divisors. I didn't word that right. Have as few divisors as possible. There we go. And highly composite numbers are kind of numbers that you look for to achieve the exact opposite, to have the maximum number of divisors that you can. And technically there is no limit. You could keep on going for bigger and bigger and bigger numbers. But if you want to look at that video, I think if you just go to YouTube and type the word anti-prime numbers and then just also type in the channel name number file, that's the name of the YouTube channel, you can go watch a video on that explaining how highly composite numbers are defined and some patterns. I think that's actually in a separate video that they link to in the first one. But the bottom line is 360 is just a number that the Babylonians chose because that was the best number they knew at the time. There's nothing inherent about circles that suggests 360. So we prefer in math to use a different measure of angles, which is the radian. So a radian is defined as a radius length. One radian equals 1 radius length. Well, length isn't the right word. Radius length isn't quite the right word, but let's try and illustrate it with numbers. I think that'll help me explain it a little better. So whatever size this circle is, if I drew the same circle, I think I want to pick a more convenient number than 85 first off. Let me draw 2 circles. Let me draw circle 1 over here with radius, how about a radius of 10? And then circle 2 over here will have a radius of, let's call that 20. And let's say that an object on each circle moves through 120 degrees. Moves through 120 degrees, so a third of a circle. So that's 120 degrees, and that's 120 degrees. So rather than defining the angle in degrees, what we can do is we can define the angle in terms of how many radii worth of arc length did you travel. This length over here. How many multiples of the radius will this be? What's nice about that is that it doesn't matter what the radius actually is. What's nice about it is that it doesn't matter what the radius actually is. So we can take the full length of, the full circumference rather. We can take the full circumference of a circle and say that this is 1/3 of a circumference, right? 120 degrees out of 360 means that this arc must be 1/3 of the circumference. Equals this arc length, I'm going to call it S. I'm going to call this S over the circumference C. So we can say then that 1/3 equals S over 2 pi r, and then if I multiply the 2 pi r over to the left hand side, then I get S equals 2 pi r over 3. So regardless of what the radius is, this 2 pi over 3, the fact that it's 2 pi over 3 multiples of the radius is what matters. So this is 2 pi over 3 times the radius, or what we call 2 pi over 3 radians. Wait, no, S is 2 pi over 3 r. Great, having brain malfunctions already. What a great way to start a stream. S is 2 pi over 3 times the radius, and this angle, we would define theta as 2 pi over 3 radians. We would say the angle of 120 degrees is 2 pi over 3 radians because it gives an arc length that is 2 pi over 3 times the radius. And that'll work regardless of whether your radius is 10 or 20 or 100 or 1 millionth or whatever you prefer. So this is basically why we prefer this radian measure. And the quick recipe for converting from degrees to radians is this. 1 radian, or no, not 1 radian, my bad. 2 pi radians. What's that? Well, that would give you an arc length of 2 pi times the radius. That would give you the full circumference. So 2 pi radians is equivalent to the angle of 360 degrees. Or if you prefer, you might want to remember pi radians is equal to 180 degrees. Either way, you can use one of these two as a conversion factor, and then whatever angle you have, just dimensional analysis like we did up here. If I want to get 85 degrees in radians, all I would have to do is take 85 degrees times, let's see, every 360 degrees is equal to 2 pi radians. Or again, if you prefer, you can write 180 over here and just 1 pi radians over here. The 2 and the 360 can simplify to 1 over 180. And let's see, 85 over 360, well, that's 17 over 72. And then times 2 pi, so that would be 34 pi equals 34 pi over 72 in radians. And I guess we can reduce, this would be also 17 pi over 36. And I could plug in the value of pi here and get whatever this actually is. It'll be some sort of nasty number with a bunch of decimals. I would rather avoid doing that. Best practice in this chapter is to hold off on substituting the value of pi. Sometimes you will see that it ends up canceling out. Other times, even if it doesn't, saving it until you absolutely have to substitute its value will just make your work cleaner and easier to read, not only for the person grading your paper, but also for you checking your work and trying to understand what your next move is. So yeah, try to maintain readability by holding off on substituting the value of pi. That will be a best practice for this chapter. Now, you might have also noticed here that there seems to be a relationship between radians and revolutions. If 2 pi radians is 360 degrees, and 360 degrees is equal to 1 revolution, then we also can directly convert between radians and revolutions. 1 revolution, which is 360 degrees, is also equal to 2 pi radians. And perhaps this is the reason why some people prefer to just remember 2 pi radians as 360, because you need 2 pi radians to convert to revolutions, so that 2 pi, remembering 2 conversion factors involving 2 pi is probably better than remembering one of them is 2 pi and the other one is 1 pi. But, it's all personal preference. You can do whatever you want as long as you don't sacrifice accuracy. As long as you understand what you're doing. And maybe with enough practice, you'll just naturally start remembering to use 2 pi here and just 1 pi here if you're going for the 180 route. But yeah, radians are going to be our preferred default unit for this chapter. Revolutions and degrees will sometimes work, but not always. They will work just fine in rotational kinematics, but once we get into some of the heavier topics in this chapter, once we get into some of the tougher stuff, a lot of that is designed to work in radians. A lot of our equations in this chapter will only work in radians, and of course I will make sure to remember, to the best of my ability, to point out which ones actually require radians and which ones will just let you use whatever. So now that we have that out of the way, let's talk about angular velocity. Angular velocity is next. Angular velocity is represented with the Greek letter omega. It's a W with a little curl in the middle. People call it W or the W thing, which is not accurate. Call it what it is. It is the lowercase omega. This is the lowercase omega. Lowercase Greek letter omega. If you want to know what the uppercase omega looks like in Greek, it's this sort of horseshoe shape. And I know some of you gamers are looking at this and going, oh, that's from the game God of War. It's the Greek capital letter omega. It's not the God of War symbol. Also, we do use this in physics as well. Capital omega is used for electricity. It is the ohm. It's used to represent units of ohms, which measure electric resistance. Basically, the higher the resistance of something with a resistance of 5 ohms versus something with a resistance of 10 ohms, a device with 10 ohms of resistance will have half as much electric current going through it than one with what did I say? Then one with 5 ohms. 10 ohms will have half as much current going through it as 5 ohms. Double the resistance, half the current, assuming, of course, that both devices are plugged into the same voltage source. But that is for a different course, so just a little taste of it. I'm not going to delve any deeper into that. Make sure you actually draw this little knot and get in the habit of calling it omega. Just don't call it W. We already use W for work. Sometimes we also use W for weight instead of F sub G, which I prefer. You will see textbooks use a lowercase w for weight sometimes. Maybe you've already seen that. So, yeah, avoid the confusion. Don't worry about sounding too nerdy. Loudly and proudly call it what it is, omega. Anyway, angular velocity is defined in a similar way to regular velocity. Regular velocity, at least average velocity, we defined as total displacement, delta x, delta y, delta s, whatever you want to call it, over change in time, change in position over change in time. Well, angular velocity is defined similarly. The average angular velocity, by the way, these are vectors. I'm not putting the arrowheads over them, but they are vectors. Angular velocity is also a vector. Average angular velocity is defined similarly as change in angular position, angular displacement, over change in time. And this is pretty easy to understand. If this thing rotates by 85 degrees, it's rotating by 85 degrees faster if it does it in 2 seconds as opposed to if it does the same thing in 20 seconds. That should make sense. I don't think I need to elaborate on that any further. So that's angular velocity, at least average angular velocity, and you can probably extrapolate from there that there's an instantaneous angular velocity, the same way there was an instantaneous regular velocity, or what we will call translational velocity from now on. And there's also constant and non-constant and average acceleration. So you can have, the same way you can have average and instantaneous and constant angular velocities, you can also have average, constant, and instantaneous angular accelerations. I had to slow down there for a second to make sure that I wasn't repeating any of them. So angular acceleration, this will be, whoops, that's an M. Angular, with an N, angular acceleration. This is also a thing that can happen. Something that's rotating could speed up or slow down in its rotation. So angular acceleration is represented with the Greek letter alpha. You have seen this before. I have used it for angles whenever theta was taken. For example, I usually try to use something like alpha or phi if I need a second angle variable. So angular acceleration, Greek letter alpha, or what some people like to call the fishy thing, because if you if you finish drawing it, if you connect this over here, that's a fishtail, and then if you draw a face and there you go, it's a fish. So yeah, some people also like to call this the fishy thing. But I'm not going to call it that, I'm just going to call it what it is, alpha. Anyway, angular acceleration. So if we wanted to define the same way we defined average acceleration as change in velocity over change in time, well, we can define average angular acceleration for a rotating object in a similar manner. We can say that it's change in angular velocity over change in time. Omega final minus omega initial over t final minus t initial, where t final will usually just be t and t initial will usually just be 0. And we can have, of course, motion with constant angular acceleration, motion with no angular acceleration, and motion with just variable angular acceleration, which would require calculus to deal with. That's a problem for the Physics C students that we will discuss at a later date. We're still just going to do everything algebra based for now, and then for the Physics C students, I'm going to go back and just review everything with the calculus added in. We've been over this before. So now, before I continue to try and write down the equations of rotational kinematics, let's go ahead and take a look at a... Oh, sorry, I didn't notice you in the chat over there. Let's see, hey, we can simplify this, slow down. Not sure what you were referring to, since I didn't catch your chat as you posted it. But if you want to update me and clarify, you can go ahead and do that while I try to pull up our simulation over here. So let me switch to this screen. And this, of course, if you haven't seen it before, this is just the PhET simulations page from the University of Colorado Boulder, as you can see right over there. If you just type PHET into Google, you'll find it. And we are looking for, we can uncheck all this. And where is it? Oh, it's probably one of their older ones. So what I want to do is, if you're not finding what you're looking for, just open this compatibility tab over here and check this. Some of their older stuff is under that. Ah, here we go. Ladybug Revolution. And we're just going to run the browser compatible version. If you want to download the Java version and just run it off of your PC offline, you're more than welcome to do that as well. And I am going to just put, let's see, we've got a ladybug and we've got a beetle. And I'm going to move the ladybug a little bit closer, like over here, and have the beetle more to the edge. And I'm going to show their velocity vector. I don't want to show their acceleration. And, oh, I guess I can't do angular acceleration in this mode. Well, that's okay. So let's give them some sort of angular velocity. It looks like they just have it in units of degrees per second, which will be fine for our purposes. Let's pick something slow, like 2 degrees per second. Okay, that's a bit too slow. Maybe Oh, never mind. There we go. It's working. Actually, I do still want it to be bigger anyway. Let's do 10. Not enough. Okay, let's do 25. Okay, that's a little bit better. At least you can kind of see the little green velocity vectors. So this is kind of what I was talking about last time with launching rockets from the equator versus launching them from closer to the North or South Pole. When you are on a planet that's rotating around its own axis, you are moving at the same velocity as the Earth underneath you when you're sitting still. The only way for your velocity relative to the ground to be zero is if you're moving at the same speed as the ground. Or same velocity as the ground, rather. And for those at the equator, since they have to go through a greater distance, they have to go the whole circumference of the Earth as opposed to someone closer to the pole who can just spin in place. They need to have a greater speed. The magnitude of their velocity needs to be larger because the distance they have to cover is also larger. We see the same thing over here with the ladybug versus the beetle. The ladybug has a much tinier velocity because it has a much smaller circle that it needs to rotate through. If they're both going to rotate at 25 degrees per second, the beetle over here has to travel faster, has a greater arc length to travel through in order to keep up with the ladybug. So from this, we see that at greater distances from the axis of rotation, while the angular velocity for both bugs is the same, their tangential velocities, their translational velocities, are different. And in fact, the relationship is going to be linear. A beetle that is twice as far away from the center as a ladybug, I didn't really do twice over here, but let's say for the sake of simplicity, let's say that this beetle is 2 times as far from the center as the ladybug, then it will actually have to move 2 times as fast. It turns out that it has to move with 2 times the translational velocity. And if you think about it, that does make sense because the distance that they have to cover is going to be whatever fraction 25 degrees is, 25 over 360 of 2 pi r. So if you double the r, you're doubling the 2 pi r, and therefore doubling whatever fraction of 2 pi r that 25 degrees per second is supposed to be. So it's a linear relationship. All you have to do is multiply by the radius to figure out what the tangential velocity is going to be given the angular velocity. Kind of. It has to be in radians first. We'll talk about that more in a bit, but first let's go ahead and throw acceleration into the mix. So here we've got the same setup, except now we have a lot more tools and controls. I'm going to put the beetle over here just so that their vectors don't overlap. And I'm going to, hold on, stop that. How do I clear the graphs? There we go, clear the graphs. I want to have a constant angular acceleration. So I want to show graphs of theta, omega, and alpha. And I'll start with theta equals 0 and omega equals 0. We'll start from rest. And I will give the platform an angular acceleration of And I guess it's in degrees or radians. I'll just keep it in degrees. I'll give an angular acceleration of 2. And are we showing... Yeah, we're showing velocity and acceleration. Okay, good. Maybe 2 would... Oh, wait, I didn't hit go yet. Okay, go. So as you can see, it starts off really slow, and then you know how acceleration works. It gradually gets faster and faster and faster. Or slower if you happen to have a negative acceleration. That's also a possibility. I'm going to have to wait for it to reach a considerable speed before we can actually see these vectors clearly. I mean, you can see them growing. You see actually two things. You see the green velocity vectors are growing, but also over there you can see that really tiny pink centripetal acceleration vector is also growing. And why would the centripetal acceleration be growing? Well, centripetal acceleration is supposed to be the square of the tangential velocity over the radius. So if the velocity is increasing, then it makes sense that the square of the velocity, and therefore the centripetal acceleration, would also be increasing. Okay, now it's starting to look a little bit clearer. I'm trying to see if there's a pause button over here. It doesn't look like it. It looks like all I can do is play and stop. Well, that's okay. There's one other acceleration that they don't show here, by the way, which is the tangential acceleration. So the tangential acceleration is a second acceleration that is going to be in the same direction as the tangential velocities that you're seeing. So imagine a third vector here, another acceleration vector that's layered on top of those green vectors for each bug. That would be the tangential acceleration, and then the total acceleration, you would have to do Pythagorean theorem between that and the centripetal acceleration, and then your total acceleration would be at some sort of angle. But I think that is all we need from this simulation, so I'm going to hit stop and switch back to our document camera. All right, so the relationship that we talked about between distance and tangential velocity. So actually, first off, I want to establish a relationship between angular displacement and not linear displacement per se, but just arc length. This is something that you already learned if you did this topic of radians in pre-calculus, but for those of you who haven't done that, it's really easy. Arc length, which I will symbolize with the letter S. This is going to be a distance and not a displacement because, well, as you can see, it's not from this point straight to this point. This would be a displacement, but this over here is clearly a distance. So arc length is equal to the radius times delta theta in radians. It has to be in radians. And this you probably figured out when I was writing all this stuff in the pink. You probably noticed it. Right over here, I had it written 2 pi over 3 times the radius. That's That's kind of the definition of radians. How many multiples of the radius is the arc length? How many multiples of the radius times the radius equals the arc length. Pretty simple, straightforward. It's kind of by design meant to work that way. Well, not kind of, just straight up by design. So similarly, we can write tangential velocity is equal to the radius times the angular velocity in radians. Well, angular velocity isn't just in units of radians. I should have actually clarified that. I knew I was forgetting something over here. If you're dividing angular displacement by time, if your angular displacement is in units of radians, then and your time is in units of seconds, then your angular velocity would be in units of radians per second. So units include degrees per second, revolutions per second, and radians per second. So when I say angular velocity in radians, what I actually mean is in radians per second. And of course, you could also have per minute or whatever, but per second is the default. Revolutions per minute, by the way, is a common one. So revolutions per minute, or RPM. Is also a common unit that you will see in book problems. Now with that out of the way, actually let's go ahead and talk about the same thing for angular acceleration. So linear, translational, or tangential acceleration will be in units of meters per second squared typically, but for angular acceleration it will be in units of degrees per second squared, or revolutions per second squared, or minute squared, or whatever, or radians per second squared is going to be our standard unit, radians per second squared. So if you have your angular acceleration in radians per second squared, then you will get your tangential acceleration in meters per second squared, or whatever units of radius you actually put in here. So if your radius is in centimeters, for example, and you multiply by radians per second squared, then you get centimeters. So you don't want to think of radians as being a unit per se. Radians are just kind of, I guess I would call them blank units. They don't actually, how do I word this? Radians are basically kind of like a proportion, or, well, not even a proportion. They're kind of like a friction coefficient. They're unitless, and they really just tell you, again, how many multiples of a radius will the arc length be for a circle that swings through the angle in question. So radians aren't actual units. It's just good to have something over here telling you what you're working with instead of just having a 1 over second squared. It's kind of like we talked about frequency in the previous chapter. We talked about how frequency is measured in units of hertz. I don't know why I have the equal sign. Frequency can be measured in units of hertz, which is also in units of just 1 over seconds, or seconds to the -1, or repetitions or cycles per second. Those repetitions or cycles are not actual units. They're more of just like a count of something. So if you replace them with some other real unit, then yeah, it's just like multiplying by 1. They just completely get replaced by whatever unit you multiply them by. So whatever units your radius has, that will be the numerator unit that replaces the radians in your angular quantities. Let me think here. Justification. So I think we saw directly through the Ladybug Revolution simulation how the tangential velocity is proportional to the radius. Also, we kind of argued it last time when talking about launching rockets from the equator, but we can go through the reasoning again. So let's say we have an object that starts over here at some radius r away from the center and starts rotating this way. It's on a surface that rotates clockwise with some angular acceleration alpha, and let's say that it starts from rest. So what's going to happen is it's going to move through some distance, and that distance, it's going to move through some distance and move through some angle theta. So whatever distance it travels through, we already showed how that's just going to be the radius times the angle given in radians. It'll just give you this arc length. For the tangential velocity, whatever velocity it has at some point has to depend on this radius as well, because if I were to compare 2 points, I didn't draw this really well. Let me think. Let me do velocity first. We'll touch this acceleration thing in a minute. Let me do velocity first. So we saw the two bugs. We've got one over here, and let's put the other one over here. And this one is at a distance of r1 from the center, and this one is at a distance of r2. And let's say they move with some sort of constant angular velocity. It doesn't matter if it's not constant, but we'll make it constant just for the sake of simplicity. So if they both move by the same number of degrees, let's say they both move 90 degrees, well then this one will have moved this distance in some amount of time, while this one will have moved 90 degrees would be this distance in some amount of time. And those distances we can calculate using S equals R times delta theta. So for object 1, S1 equals R1 delta theta. S2 is going to be equal to R2 delta theta. And they both move in the same amount of time, so V1 is simply going to be, well, I guess this wouldn't be velocity per se, but it would be speed. So I won't put the vector symbol over it. Speed 1 is just going to be distance 1 over time 1, and speed 2 is going to be distance 2 over time 2. Time 1 and time 2 are the same. These two objects, whatever they are, two bugs on a rotating platform or whatever you would like to imagine them being, they rotate through the same number of degrees in the same amount of time. So their t's are going to be the same. So if I simply replace S1 and S2 with R1 delta theta and R2 delta theta, then what do I get? I guess I'll write it over here since it's getting kind of crowded down there. So I get V1 equals S1, or no, not S1, R1 delta theta 1 over time, while V2 equals R2 delta theta 2 over time. And delta theta 1 over time, well, that's just the angular acceleration. Delta theta 1 over time and delta theta 2 over time, they both have the same delta theta. And delta theta over time, that's just going to be your constant angular velocity here. So we get equals R1 and R2 times delta theta over t is omega. And there you go. So now we've proven it for velocity, and then you can follow similar reasoning for angular acceleration to tangential acceleration. You could follow similar reasoning to prove that. If these two objects speed up because their platform is speeding up, then they would speed up at the same rate in terms of degrees or revolutions or radians per second squared. They would have to have the same angular acceleration, they'd have to have the same alpha, and if they started with the same angular velocities, if they both started from rest, then we could simply say, let me switch colors because this is starting to get a little hard to follow. Then we could say A1 is equal to, let's see, is equal to V1 over T is equal to, well, we already established that V1 is equal to R1 omega, or rather, no, hold on, I did that wrong. A1 is equal to delta V1 over T equals V1 final minus V1 initial over T, V1 final minus V1 initial over T. And V1 final and V1 initial, well, V1 we already proved is simply the radius times the angular velocity, so V1 final would be R1 times omega 1 final minus R1 times omega 1 initial. You can factor out the R from that, and you get A1 equals R1 times omega 1 final minus omega 1 initial over time. That is just going to be the angular acceleration. And then you could do similar for object 2. Yeah, I don't know what I was trying to do over there. I was overthinking this. But there you go. Probably more than you ever wanted to know about these relationships, but hopefully now you find these three to be convincing. Oh goodness, is orange drying up? No, there's still ink in there. There we go. So yeah, remember these three. We are going to use them a lot. Make sure you remember them. Very, very important. What is that symbol on my chat bar? Oh, I see. That's what it is. Or chat bar. I don't... Chat window. It's because my mouse was hovering over... There's this graph that you see while streaming live in your live control center, in case you've never done a live stream on YouTube before. That kind of just goes up and down as people come in and out of the stream. That's what it was. It was just hovering over one of them. Anyway, I want to go over what next. Well, now that we've established these three relationships and defined the concepts of angular displacement, angular velocity, and angular acceleration, let's talk about rotational kinematics. Or rather, the equations of rotational kinematics, I should say. We've been talking about rotational kinematics this whole time. The equations of rotational kinematics, specifically for constant acceleration. Equations of constant angular acceleration, or the equations of rotational kinematics. They will not surprise you at all. If average angular acceleration is defined as the change in angular velocity over change in time, well, that kind of lines up with how we defined it for linear acceleration. And if the acceleration is constant, if you have a situation where angular acceleration is constant, then the average acceleration is that constant. If alpha is constant, then alpha average just straight up equals alpha. That should make sense if you have a constant acceleration, if you have it on a graph. Actually, do I still have the graphs? Yeah, I do still have the graphs from the Ladybug Revolution, so let's look at that real quick. So here you see the angular velocity is just going up in a straight line. Well, I guess it doesn't look that straight just because of hardware limitations, I assume. Or hardware. Yeah, I guess, yeah. Hardware limitations, that's what I'm going to call it. You only have so many pixels on the screen to work with, so sometimes your graphs are going to look jagged even though they're supposed to be straight lines. I mean, that is supposed to be a curve, and you might find these shapes to be rather familiar. You might find these shapes to be rather familiar. This one seems to curve up like a parabola. A very flat parabola, but a parabola nonetheless. Can I? Oh, I did not mean to do that. Okay, there we go. I thought that would just get rid of all this information on the top so we could see more of the graph, but oh well. So yeah, you see the angle seems to be some sort of parabola. The angular velocity seems to be some sort of straight line going up. And the angular acceleration, if I zoom in just enough to show that it's not at 0, yeah, not at 0, it's the graph of some constant. It's just a straight horizontal line. This should look familiar. This is the series of graphs that we get for an object accelerating from rest with regular acceleration. So you shouldn't be surprised with what comes next. If the angular acceleration is constant, then the average acceleration is the angular acceleration. The graph of the angular velocity versus time will be some sort of straight line, and the instantaneous angular acceleration at any given point, the slope of the tangent line at any given point, well, all the points on this graph have the same slope. The slope is constant, as opposed to a graph with variable angular acceleration, which would have more curves to it and stuff like that. And over here, well, now you've got instantaneous angular acceleration will be the slope of that line for that point, and then at this point in time, the instantaneous angular acceleration will be that, something closer to 0, and then, for example, over here, it would be negative slope. And if you wanted to get the average between 2 points, let's say between this point and this point, let me use a third color for that, then you would just calculate the slope of this dotted line instead. And as you can see, the slope of this dotted line does not match necessarily all these other slopes that you're getting at all these other points. But if the angular acceleration is constant, then your omega versus time graph is going to look like this. It's going to look like a straight line. And at that point, yes, omega final minus omega initial over time final minus time initial is constant, is whatever this angular acceleration is supposed to be. So then we can say alpha is equal to, well, omega final minus omega initial over time, and if I multiply by time, I get alpha times t equals omega final minus omega initial, and if I add omega initial to both sides, I get a familiar looking equation, omega initial plus alpha times t equals omega final. I'm going to write the omega final over on this side. Oh, what is this? Ta-da! It's just the regular first kinematics equation, but we've substituted translational velocity with angular velocity, and we've substituted translational acceleration with angular acceleration. A lot of the equations in this chapter are going to be just equations you learned before, where we are substituting variables with their rotational versions. So if you've been memorizing your equations up to this point, at least all of them except for the ones I specifically told you that you don't need to, then you're not going to have a hard time learning all the new equations of this chapter. And there's a lot of them, because we're talking about, what, 5-6 chapters worth? So yeah, if you haven't been doing that, then God help you, because it's going to feel like drinking out of a fire hydrant. some of the equations are not going to be just rotational versions of old equations. We are going to have a few brand new ones. But if you already know all the old ones, then it'll be easier to add a few new ones on top. Won't be so easy, however, if you're trying to relearn the old ones on top of learning the new ones. But that's our first equation of rotational kinematics, and I'm not going to go through the entire proof for the other two. You can just follow the same steps I did with regular kinematics. You can say the area under the curve of an angular velocity versus time graph is going to be angular displacement, and you can argue for that by saying, well, if the angular velocity was constant, then you could just multiply that angular velocity by time to get the angle through which the object rotated. If the angular velocity was 25 degrees per second for 4 seconds, for example, degrees per second for 4 seconds, then you can say that the area of this rectangle, its height is 25, its width is 4, and that would give you an area of 100, which is the 100 degrees that it would have rotated in 4 seconds. And then from there you can say when it's not constant, it should still stand to reason that area under the curve would be whatever the angular displacement is, and divide it into a rectangle and a triangle and do all the stuff that I did way back when we were doing kinematics, and then combine the equation that you get from this with the first equation to eliminate time and derive your third one. You can go through all those steps if you really, really want to. I suppose it wouldn't hurt. But I'm just going to go ahead and say angular displacement equals omega initial times t plus 1/2 alpha t squared, which is the equivalent of delta x equals v initial t plus 1/2 at squared, or delta y, or whatever. And then omega final squared equals omega initial squared plus 2 alpha delta theta is your rotational version of v final squared equals v initial squared plus 2a delta x, or delta y, or whatever the case may be, whatever your linear displacement variable happens to be for the problem. So there you go, your 3 equations of kinematics. If you already remember the 3 from regular kinematics, then these are really just a mindset change more than anything. The pattern is exactly the same. Now, the units here do not have to be in radians. Your rotational units do not have to have radians in them. They will work just fine in degrees or revolutions as long as they all agree with each other. So for example, it won't work if my angular velocities are in radians per second, but my angular acceleration is in revolutions per second squared. That's not going to work. You have to get the units to agree with each other, at least for your known values, and then your unknown values will just come out in whatever units you put in. So if delta theta is unknown, but I have omega initial and alpha in, for example, revolutions per minute and revolutions per minute squared, then my delta theta will come out in revolutions, assuming that my time is also in minutes. So yeah, as long as your known variable values agree with each other, your unknown variable units will come out to agree with them as well. If in doubt, default to radians. Whenever you're not sure what you should use, just use radians. If the problem doesn't specify, just use radians. Unless you see something where, for example, oh, if I keep this in revolutions, it'll be a nice round number, but if I try to convert it to radians, it'll become a hideous decimal. In that case, if the problem doesn't specifically require you to use a specific unit, then yeah, just go by what might look nicer on paper. That is not a bad idea. But if you're not sure, or if you're overwhelmed by having 3 different choices when a problem doesn't tell you what units it's expecting, just default to radians. Okay, how about we do some problems? How about we do some problems before we look at some other equations that are affected by this new understanding. Let me pull some from the book. They're going to be pretty simple. I mean, it's just a review of kinematics, and I did say up front this lesson was going to be the easier part of the chapter. Let's have a look. So, here's a good one I like to start all my students off with. It says, find the angular speed of Earth about the Sun in radians per second and degrees per day. And that's all the information it gives you. What? Find the angular speed of the Earth around the Sun in radians per second and degrees per day. Omega of Earth around the Sun in radians per second and degrees per day. What on earth? I wasn't given enough information. That is a common reaction to this question. But you do have enough information. I said this last time. Common knowledge. When we were talking about planetary motion last time, I emphasized this. I emphasized it for a reason. You didn't think we'd be seeing it again so soon, did you? How many radians, or degrees for that matter, does the Earth go through in a given amount of time? You know what that number is for a specific amount of time. Let's assume a full year. How many degrees does the Earth go around the Sun in a full year? 360. And the amount of time is 365.25 days, which we will have to convert, but otherwise this problem isn't too bad. It's just an exercise in conversion. So I'm going to start with degrees per day, actually. So omega Earth equals 360 degrees over 365.25 days. Don't forget the 0.25. We have leap years every 4 years for a reason. And this one should be easy. It'll be slightly less than 1. 360 over 365.25 is about 0.9856. 0.9856 degrees per day. Okay, easy enough. Now we need to convert this to radians per second. Well, 0.9856 degrees per day. Let's start with converting the degrees. 360 degrees is equal to 2 pi radians. Don't forget the pi. That cancels out your degrees and gets you radians in the top. We're done with the angle units. Now for the time units. 1 day is equal to 24 hours. So that cancels your days and gives you hours in the bottom. And then 1 hour is equal to 60 minutes, and 1 minute is equal to 60 seconds, or you can just skip ahead to 1 hour equals 3,600 seconds. Or, better yet, if you remember from last time, 1 day is equal to 86,400 seconds. That's what 24 times 3,600 will give you. And I guess since we already have all these crazy decimals anyway, we might as well plug in the value of pi here. Yeah, I mean, at this point, what are we even trying to prove by not substituting the value of pi? There's nothing to prove here, so I'll go ahead and substitute it. 0.9856 times 2 pi divided by 360 and divided by 24 and divided by 3,600 is a very tiny number. Let me actually switch to scientific notation for this. Mode scientific, and then redo that calculation. 1.99 times 10 to the negative 7. I'm getting about 1.99 times 10 to the negative 7 radians per second. Does that make sense? Well, it was already really tiny to begin with, and yeah, we did divide it by something on the order of 100, and then by something on the order of 10,000. So yeah, something times 10 to the negative 6 or 10 to the negative 7 does make sense to me. Okay, I believe it. I believe it. And there you go. So it was really just an exercise in unit conversion and an exercise in applying common knowledge. Yes, the AP Physics exam does expect you to know that there are 365.25 days in a year, and that it takes a year for the Earth to go around the sun. Outrageous, I'm sure. I can't wait for people to go out there and protest College Board. Next question. Says a potter's wheel moves from rest to an angular speed of 0.2 revolutions per second in 30 seconds. Find its angular acceleration in radians per second, or radians per second squared. You can mix your time units. You could have an acceleration in radians per second per minute, for example, or something like that. It's not the most convenient unit for physics problems, but we talked about it before, I think. I would hope I mentioned it before in car commercials when they say that their car goes from 0 to 60 in 3 seconds or 4 seconds or whatever. That's 0 miles per hour to 60 miles per hour in, let's say, 4 seconds. That would be an acceleration of 60 divided by 4 is 15 miles per hour per second. So in 1 second, it goes from 0 to 15. In the second, it goes from 15 to 30. In the third second, it goes from 30 to 45. And in the fourth second, it would go from 45 to 60 miles per hour. It does make sense when you slow down and think about it. You can have a mix of two different time units for your acceleration. But fortunately, they don't want that here. So they said, I'll read it again. A potter's wheel moves from rest, that means omega initial equals 0, to an angular speed of 0.2 revolutions per second in 30 seconds. Omega final equals 0.2 revolutions per second. Did I? Yeah, I did mention it. It just reminded me of revolutions per minute, and I wanted to make sure I mentioned that. Anyway, so that was in 30 seconds. T equals 30 seconds. Find angular acceleration in radians. Oh, wait, it only wants it in radians per second. Did I misread it the first time? I guess I did. Find alpha equals what? And then in radians per second squared. Okay, well, time is already in seconds, so we're good there. Omega initial is 0, so it'll be 0 in any units, so we don't have to convert omega initial, thankfully, but we do have to convert this from revolutions to radians. We don't need to convert the seconds, but we do need to convert the revolutions. So that'll be omega final equals 0.2 revs per second. Every 1 rev is 2 pi radians. That'll be the thing to memorize for this lesson. Your conversion units between radians, revolutions, and degrees. You should be able to convert between any of those three into any one of the others. You should know how to go from radians to revolutions and vice versa. You should know how to go from radians to degrees and vice versa. And you should know how to go from revolutions to degrees and vice versa. Anyway, this is going to be 0.2 times 2 is 0.4, so that'll be 0.4 pi. 0.4 pi rads per second. Now that we have that, we can get the angular acceleration simply using the first equation. First equation of rotational kinematics gives us omega final equals omega initial plus alpha times t. We are assuming a constant angular acceleration after all. Subtract omega initial, which, well, it's 0, so there's nothing to actually subtract here. And then t is 30, so 0.4 pi equals alpha times 30. 0.4 over 30 is 0.2 over 15. Okay, that's going to end up being a decimal anyway, so let's plug in the value of pi. 0.2 pi over 15, or 0.4 pi over 30 if you prefer. That's going to be... My calculator was still in scientific mode for a second there. 0.0419 is what I will round it to. So I get alpha equals 0.0419 radians per second squared. Next question says, a dentist's drill starts from rest. After 3.2 seconds of constant angular acceleration, it turns at a rate of 2.51 times 10 to the 4 revolutions per minute. Find the drill's angular acceleration, it never specifies the units here, and determine the angle in radians through which the drill rotates during this period. Well, since part B is going to be in radians anyway, then we might as well do part A in radians as well. So part A, find the drill's angular acceleration. Let's draw a line to separate off this next problem. And let's see what we can do. I guess I haven't used this one in a bit. So T, I'll just write all my given information over. Actually, I'll write it over here. T equals 3.2 seconds. So, and they did say it starts from rest, so omega initial is 0. And they also gave us omega final is 2.51 times 10 to the 4 revolutions per minute. And I think I would rather just write that out in normal notation, so 25,100 revolutions per minute. RPM, if you see it written as RPM, that just stands for revolutions per minute. All right, we need to, we don't have to convert that to radians for the first part, which says find the drill's angular acceleration, but we might as well, because we're going to have to do a conversion in the second part anyway, and that conversion will be much easier if you find the angular acceleration in radians per second squared. Because if we do it right now without converting, we're going to get angular acceleration in revolutions per minute squared. And converting minutes to seconds right now would be easier than converting minutes squared to seconds squared later. It's still doable, but I would rather not have to deal with converting squared units if I don't have to. So let's go ahead and get the angular acceleration. I'm getting my steps out of order. Let's go ahead and convert first and then get our angular acceleration. So convert revolutions per minute to radians per second, 25,100 revs per minute. If I convert my minutes to seconds, that would be 1 minute in the top equals 60 seconds in the bottom. And then 1 revolution is equal to 2 pi in radians. And that cancels revolutions and gives me radians on top. 25,100 times 1 times 2 pi over 60. So I'm going to go ahead and do 25,100 times 2 over 60 and hope that's a nice number. Actually, it won't be. 25,100 times 2 over 60 is 836 point repeating sixes. So 836 and 2/3. 836.667 pi radians per second. Well, it's not too hideous right now, so I'll keep the pi unsubstituted for now. So that gives me omega final in radians per second, and then to get the angular acceleration, we follow pretty much the same steps we did in the previous problem. Omega final equals omega initial plus alpha times t. Omega initial is 0, just as it was in the previous problem, so just divide by t. So 836.667 divided by 3.2 is 261.458. 836.667. Yeah, 261.458. So angular acceleration equals 261.458 times, of course, the pi, and that will be in radians per second squared. If I go ahead and multiply the pi into that, let's see what we get. I get 821.396. 821.396 with the pi substituted. Either of those answers would be fine. Let's look for another one. Well, that one's decelerating, so that might be nice to look at. Oh, here's a good one. So it says the tub of a washer, and I suppose I'm going to want to start this on a new page. It says the tub of a washer for clothing goes into its spin-dry cycle, starting from rest and reaching an angular speed of 5 revolutions per second in 8 seconds. At this point, the person doing the laundry opens the lid and a safety switch turns off the washer. The tub slows to rest in 12 seconds. Through how many revolutions does the tub turn during the entire 20-second interval? Assume constant angular acceleration while it is starting and stopping. So we have, if I were to graph this as an angular velocity versus time graph, we have it starts from rest. Let me use a different color here. It starts from rest, reaches some sort of speed in, what was it, 8 seconds? Yeah, in 8 seconds. And then in another 12 seconds, it comes back to rest. So if that's 8, then that would be another 8. And then half of that. So that would be the 12-second mark. It reaches some sort of speed. Then the person opens the lid, which causes the safety switch to immediately turn it off, and it slows down and comes to a stop. Okay, this peak over here is at omega equals 5 revolutions per second. If you do these conversions often enough, especially from revolutions to radians, that should be a really quick calculation with enough practice. A revolution is 2 pi radians, so 5 revolutions is 10 pi radians. Equals 10 pi radians per second. Let's see, so starts from rest, reaches angular speed of 5 revs in 8 seconds. At this point, the person doing the laundry opens the lid and the safety switch turns off the washer. The tub slows to rest in 12 seconds. Through how many revolutions does the tub turn during the entire 20-second interval? Oh, well, if it wants it in revolutions, then I don't even need to convert to radians this time. Okay. That works for me. So here we've got a 2-leg problem. We've got leg 1 is a positive acceleration phase, and then leg 2 of this object's motion is a deceleration phase. So we have, let's see, omega 0, I'll call it, is 0. Omega 1 is 5 revolutions per second. Angular acceleration 1, we don't know yet. Angular displacement 1, we don't know yet. And time 1, we do know, is 8 seconds. And then for the second phase, omega 1, which is 5 revs per second, omega 2, which is 0, alpha 2, which we don't know, but we expect it to be negative, and delta theta 2, we don't know, and T2 is 12 seconds. Well, we have 3 of our 5 kinematic variables for each part, so we can just go ahead and calculate the other 2. And it looks like we're going to do the same process for each phase. So I need to find, there is no way to get delta theta 1 without finding alpha 1 first, because all of our equations have the angular acceleration in them. So if we don't find this, we're going to be stuck with 2 unknowns, no matter which equation we choose. Well, there is one way to avoid that, which is we could use the fourth equation for constant acceleration. Since the angular acceleration is constant, that means that the average velocity, the average angular velocity, is the average of the velocities. When alpha is constant, you might remember in regular kinematics, when the acceleration is constant, the average velocity is the average of the velocities. The same holds true here. When alpha is constant, omega average is just equal to omega initial plus omega final over 2. Only for constant angular acceleration. If it's not constant, then you can't do that. Now, the angular acceleration here isn't constant for the entire 20-second interval, but it is constant for each section of the motion. It is constant for this phase, and then for this phase, it's constant. So as long as I keep those phases separate, I can use that. I can say that my total angular displacement is equal to omega initial plus omega final over 2 times time. So my fourth kinematics equation that I could use when I don't know alpha is 1/2 omega initial plus omega final times t equals delta theta. That is something I could do. But I'd rather just calculate the angular accelerations anyway, because I want to make sure that this actually comes out negative, since we haven't seen that yet. So let's use first equation to calculate angular acceleration, and then second equation to calculate delta theta 1. And I guess we'll use third equation for delta theta 2 just so that we actually have an example of using the third equation, since we haven't done that yet either. So omega final equals omega initial plus alpha times t, omega initial being 0, 5 revolutions per second equals alpha times 8. So that gives us 5 over 8 is what? 0.625 revolutions per second squared for your angular acceleration, at least for your first one. And I shouldn't have called it omega final, I should have called it omega 1 and omega 0. Perhaps I scheduled this stream too late in the day. Now that we have that, we can go ahead and use second equation. Delta theta 1 equals omega 0 times t1 plus 1/2 alpha 1 t1 squared equals, well, that's going to be a 0. And then 1/2 0.625 times 8 squared. Well, 0.625 was 5 over 8, so 5 over 8 with 8 squared. One of the 8's cancels and you're left with 5 times 8. And then times 1/2, so that's 5 times 4, that's 20. Equals 20 revolutions. All right, and then next part was finding how many revolutions it goes through in the slowdown phase. So similar math. Let me switch colors. So we would do omega 2 equals omega 1 plus alpha 2 t2. 0 equals 5 plus alpha 2 times, that is not 12. That is supposed to be 20, and this distance between them is supposed to be 12. Sorry to the people who were probably screaming at me through the screen for that one, but hey, better late than never. At least I caught it. I have said time and time again that there is no such thing as reaching a level where you don't make mistakes, but there is such thing as reaching a level where you become really, really good at catching mistakes. It's all about developing good habits. Anyway, T2 is still 12 seconds, regardless of what my graph was incorrectly stating over there. And that's going to be alpha 2 equals negative 5 over 12. Subtract the 5 and divide by 12. And I think I'm going to keep it as negative 5 over 12 here. So alpha 2 equals negative 5/12 revolutions per second squared. Probably should have allotted more space for that. And then for delta theta 2, let's go ahead and use the third equation for this. So omega 2 squared equals omega 1 squared plus 2 alpha 2 delta theta 2. Omega 2 squared, that's 0, equals omega 1 squared, that's 5 squared, plus 2 times negative 5 over 12 times delta theta 2. Okay, that's going to be negative 25. Equals, that'll be negative 5 over 6 delta theta 2. The negatives cancel, the 5s reduce and multiply by 6. 6 times 5 is 30, so delta theta 2 is 30 revolutions. And then delta theta total is just 20 plus 30. So it completed exactly 50 spins between speeding up and slowing down to a stop. For those of you wondering why this is not a negative 30, just because the acceleration is negative doesn't mean that the direction of motion instantly turns negative. It just means it's slowing down, still moving in its positive direction, whatever positive means here. Clockwise, counterclockwise. It's all personal preference, really. Kind of like what we did with momentum, where it didn't really matter what you picked as long as you specified one direction to be positive and the other to be negative. If you need a default, then the default, at least from math class, from your pre-calculus trigonometry class when dealing with angles, is that counterclockwise is actually the positive direction for measuring angles. But we're not going to worry about that in this course. Do I have any other good ones here? I mean, I think with the examples we've seen so far, the point has been driven home. It really is just regular kinematics, but replacing the translational versions of the variables with their rotational analogs. Analog, that's a word for you. Analogs. Things that parallel each other, kind of like how an analogy tries to explain one thing by comparing it to another thing and using whatever logic applies to that other thing to help understand the first thing. This also might introduce you to another term, which is analogical thinking, which we are going to do a lot of in this chapter. Analogical thinking, and have done a lot of. Analogical thinking, thinking in terms of analogies, thinking in terms of things that are similar to each other and have some sort of transferable logic from something else we already understand. Analogical. I need to stop giving out these mini English lessons of the day before I start getting a bunch of people asking me to tutor them in English. Oh, God, no. I think I'd rather teach programming, and that's something I avoid. Any other good or important problems? I'm just looking through here real quick, just making sure there's nothing with some fancy twist in it. Oh, right, of course. How could I forget? We didn't do a single example of converting from rotational to translational. Let's do that real quick then. So this one says a coin with a diameter of 2.4 centimeters. Be careful about the wording there. Diameter, not radius. A coin with a diameter of 2.4 centimeters is dropped on edge onto a horizontal surface. The coin starts out with an initial angular speed of 18 radians per second and rolls in a straight line without slipping. We'll talk more about what it means to roll without slipping in a later part of this chapter, but for now, don't worry about it. If the rotation slows with an angular acceleration of magnitude 1.9 radians per second squared, how far does the coin roll before coming to rest? How far? This is asking about linear distance. This is asking about a linear distance. So omega initial is 18 radians per second, and it comes to rest at some point, so omega final is 0, and the angular acceleration, they said it slows with an angular acceleration of 1.9 radians per second squared, so we need to remember to include the negative sign, negative 1.9 radians per second squared. And then the question is, how far does it roll before coming to rest? How far does it roll? How far? How much? It's asking for magnitude. How far does the coin roll? So we can draw it, of course. Here it is. It'll be rotating like so. I guess I have a use for this now. This is a yo-yo. I bought it a couple weeks ago because one of my students asked me about how yo-yos work, and I wasn't entirely sure myself, so I decided to buy one and just observe in real life, and I learned some new things from it. I learned how a yo-yo actually catches onto the string and climbs up the string. Well, a modern yo-yo anyway. But yeah, so if this yo-yo, luckily it has a convenient string here that helps us measure distance, if this yo-yo rolls one revolution, so the way I'm going to tell that it rolls one revolution is I'm just going to wait until this butterfly symbol is back in the same position that it started as. Not that it's really going to matter to you guys, but if I roll through one revolution, which is about that far based on the position of the symbol, then the amount of string that rolled out, well, if it was actually flat on the page, the amount of string that rolled out would measure the distance that it rolled. Again, assuming that the string rolls out laying flat on the page. So that distance of string that rolled out is also going to be what? The distance around the axle of the yo-yo, which I guess for a yo-yo, the yo-yo is probably not a good example because as the string unwinds, you get the radius starts off really small around the axle and then just kind of, you don't really have a constant radius, so maybe not the best example, but the point I'm trying to illustrate here is that if this coin rolls one time, if it completes one revolution, then the distance it traveled by the time it makes one 360-degree turn, one revolution of rolling is going to be 2 pi r worth of distance traveled. It's going to be one circumference of distance traveled. So if we just count what angle it rotates through, if we just calculate delta theta of the coin and then convert that to distance, figure out what arc length it traveled through, we'll be good to go. So the strategy is simply find delta theta, then use S equals R times delta theta in radians to find distance. That's the strategy. Not too hard to do. We'll save it for later. I was going to start off by changing this to radius, but we'll worry about that in the end. So everything else is already in radians, which is very convenient for us. All we really have to do is I think I would rather use the third equation here since we don't know t. Yeah, third equation would be best. So omega final squared, which is 0 squared, equals omega initial squared, which is 18 squared, plus 2 alpha delta theta, so plus 2 negative 1.9 delta theta. This delta theta is going to come out in radians because everything else was radians as well. So 2 times negative 1.9 would be negative 3.8, and then negative 18 squared. I believe 18 squared is 324. Yep. So negative 324 equals negative 3.8. Cancel the negatives. And 324 over 3.8 is 85.263 approximately. So delta theta is about 85.263 radians. And then since arc length is equal to radius times the angle in radians, all we have to do now is multiply by 1.2. If d is equal to 2.4, d is equal to 2r, so r is equal to 1/2 of d, so 2.4 centimeters equals 2r. r is equal to 1.2 centimeters. We don't actually need to convert the centimeters to meters here. If I do r times delta theta, as long as delta theta is in radians, I mentioned this earlier, whatever you multiply your radians by, those become the new units. So 1.2 centimeters times 85.263 radians, I'm going to get centimeters. I'm just going to get the regular distance in centimeters. So S is going to be 1.2 times 85.263. 1.2 times 85.263 is 102.3156. I'll round it to 0.32, so about 102.32 centimeters. And it never specified that we had to do it in meters, so we're good there. But if you do want to convert it to meters, it is pretty nicely just over a meter. And now that we have done that, we've got one last thing to talk about before we wrap up this stream, and that is, how does our understanding of circular motion change in light of all this? Let's start with uniform circular motion. So uniform circular motion, the only major change here, is that we have one more way to calculate centripetal acceleration. If centripetal acceleration is equal to v tangential squared over r, then since v tangential is equal to r times angular velocity, we can use angular velocity instead of tangential velocity. We can say v tangential is r times omega, and then we're squaring that. If I square that, then I get r squared omega squared over r. One of the r's reduces, and I'm left with r times omega squared. So another equation for centripetal acceleration is r times omega squared, and another equation for centripetal force is mr omega squared. Now, does this equation really do much for us? The only thing it does for us is it saves us a bit of time if your information is already given in angular terms instead of translational terms. If you're given the angular velocity, then using r times omega squared is faster than taking a step to convert the omega into a v. But otherwise, it doesn't really do anything for you that, like solves a problem that you couldn't solve before. If you have the means to calculate the centripetal acceleration given omega, then that means you by necessity know what the radius is. But if you know what the radius is, then you can calculate v. So it's not really adding anything except for maybe saving you a step, depending on whether the problem gives you v or omega to begin with. But either way, the problem would also have to give you r to find the centripetal acceleration. So nothing super revolutionary going on here, just an alternative that might save you a single multiplication or division step. And I suppose the other thing it does do is that it does show you that the centripetal acceleration needed for an object increases with the distance of that object from the center. So I guess it has a conceptual value. If we're talking about a bunch of things that are moving with the same angular velocity, this tells you that the objects that are further out for the same angular velocity actually require a greater centripetal acceleration. And that might seem contradictory, because didn't we say that greater distance means you have a lower centripetal acceleration requirement? Yes, but this is from the perspective of you've already decided ahead of time what you want your angular speed to be. This is basically reinforcing what we saw with the ladybug and beetle situation earlier today. The one that's further out needs the greater centripetal acceleration for the same angular speed, right? I froze these guys at some moment in time. Notice the centripetal acceleration on the beetle is much larger than it is on the ladybug. That's because the V tangential on the beetle has to be larger in order for it to have the same omega as the ladybug. So we're not cheating the rules here or anything. We're just working under a different rule. The rule being all objects on this rotating plate, turntable, whatever you want to call it, have to have the same angular speed, which by necessity means objects further out have to have a greater tangential speed, which then tells you that they have to have a greater centripetal acceleration. So it is all consistent. If that kind of just made your head spin right there, give it some time and think through it. Like, sleep on it, come back the next day, look at it again, and open up this simulation and run it yourself and really think about it. It will make sense. Just give it some time to sink in. So that is one change for circular motion. The other change, or the other new thing that we can do with circular motion now that we know about rotational kinematics, is we can calculate tangential acceleration and calculate the total acceleration on an object that is not in uniform circular motion, but accelerated circular motion instead. So let me get a fresh new sheet of paper. And let me see if I even have a problem in this book that has accelerated circular motion. I might not. Maybe it's in the other chapter because, well, I mean, I could always just come up with one for myself. Yeah, I think that's exactly what I'm going to do. Let me just come up with something real quick. So let's talk about an object in accelerated circular motion. Accelerated circular motion. This is closer to what you actually experience when in a car. This is closer to what you actually experience in a car. You typically go around corners in a car by slowing down as you go into the turn and then speeding up as you go out of it. Or if we're talking about getting onto a highway, you get on really slow. You take the on-ramp to the highway, and you build up speed, and then you get onto the highway, you merge onto it and start moving with all the other vehicles. This is a terrible drawing, but let's say these are a bunch of lanes on some sort of superhighway. Ironically, the more lanes there are on a highway, the more congested the traffic becomes. There's a video on that. Actually, the same channel that I linked a few streams ago for collisions with trucks and stuff, I had an iCard that linked to a video from this channel, not just bikes. And also, there's a spring problem. There's a problem involving springs that was covered by another YouTube channel, Steve Mold. So if you look at not just bikes, and his video on, I don't even remember the title of the video, but basically it's the one where he talks about how wider highways lead to more traffic, not less. And also Steve Mold, he does a lot of physics stuff on YouTube. He has this, I think it was called the spring paradox. I'll probably just link both videos in an iCard or the description, or both, where he cuts a string connecting two springs, and that physics demonstration is kind of similar to what happens with highways. But now I've gone off on quite the tangent. So yeah, that stuff, I'll put it in the description or in an iCard or both once I get around to time-stamping this stream in post-production. Anyway, what was the problem that I was going to do? So when you get onto a highway, you start pretty slow and you go in this somewhat circular path and you accelerate, you speed up. Your tangential velocity increases. You don't go in uniform circular motion, you go in accelerated circular motion. So you have a constantly increasing need for centripetal acceleration the faster and faster you get. And of course, if you accelerate too hard and you get too fast, if this curve, if this on-ramp is not a wide enough turn, then you can't really speed up that well. There's a reason why these are really, really, really wide arcs, wide loops. It's to allow you to reach really high speeds so that you can come onto the highway without disrupting the traffic that's already there behind you, without having to force them all to slow down for you in order to avoid a collision. Faster is actually safer, as long as it's not too much faster, of course. And that reminds me of yet another video. Oh my goodness. Another video about traffic from CGP Grey. Okay, that's 3 things I'm going to have to link to. I won't talk about it any further than that. I'll just link to it and let's move on with our problem. So let's say that you are in a car and you want to speed up during a turn, and let's say that it's, I don't know, a 120-degree turn, right? You don't go in a full circle on an on-ramp. You go in some sort of circular arc. You go in part of a circle, let's say about 120 degrees worth. So I guess I don't really want to attach numbers to this problem. I really just want to highlight what's going on. So you're going to have, at any given time, let's say you start over here, and sometime later you're over here, so you're moving in this direction. You are at some velocity already, let's say when you go onto the ramp, so this is going to be v initial, and then when you get off of the ramp and onto the highway, you're going to be at some speed v final over here. And all along the way, you're going to have both a centripetal acceleration that keeps you on the circular path and a tangential acceleration that helps this v initial grow into this v final. So let's say at some other random point, let's say over here, for example, you have two accelerations on you. You've got your centripetal acceleration, but you also have your tangential acceleration. And in this case, if you're speeding up, then your tangential acceleration would be in the direction of your tangential velocity. So that's your A tangential. And then you've got your total acceleration, which would be just the vector sum of these two. Your total acceleration would be this. So this is a total. That is not very legible, but it says total, I promise. So if you are uniformly speeding up from v initial to v final, then all you have to do to get this A tangential is take r times your alpha. So just take your alpha would just be your v final minus v initial divided by the time that it takes to get from v initial to v final. Multiply that by r, make sure your alpha is in radians, of course, and I guess this would be per second squared if we're talking about getting onto a highway. Units of seconds make sense. It takes seconds, not minutes or hours, to get onto a highway. Well, I guess that depends, because maybe that's not so true in LA. I hear a lot of bad things about traffic in LA and also in New York City, at least at specific times of the day. But yeah, take your R alpha, that'll give you your A tangential. Your A centripetal is just going to be your R omega squared or V squared over R, either way. I think R omega squared would actually make more sense to use here. Let's use the R omega squared version. And then for this alpha, let's say that it's a constant acceleration, which would make it omega final. Yeah, which would make it omega final minus omega initial over t. So let me see, what can we do with that? Is there anything interesting we can do? I don't think so, but, well, A total is going to have a magnitude of just square root of A tangential squared plus A centripetal squared equals the square root of R squared alpha squared plus R squared omega to the fourth, right? if this is r omega squared and then I square that, r squared and omega to the fourth. Yeah, I don't know. I feel like there might be some interesting discovery here, but I'm not seeing it yet. Who knows? Maybe if I think about it later, I'll discover something, but I'd rather not try and just aimlessly wander with this. There might not be anything here, so I don't want to waste time, chasing what might not be there. The point is that the acceleration on an object that's moving in a circular path is not necessarily perpendicular to its motion. It could be at an angle to its motion that is, I guess it would be more biased towards the perpendicular direction to its motion, but it really just depends on how big this angular acceleration even is. And the other thing to take away from this would just be that centripetal acceleration in this case is not constant. Centripetal acceleration is not constant, so the total acceleration then would also not be constant. Over here, the tangential acceleration is actually the only constant one. That would be a constant component. This would actually be growing, so this omega over here would be a function of time. Let me see. So omega equals some omega initial, I'll call it omega 0, plus alpha t. So if I factor out the r squared, and then this will be omega 0 plus alpha t all to the fourth. Is there anything of interest here? I don't want to FOIL this. Maybe it would be more fun to FOIL if omega 0 was equal to 0. Yeah, I don't know. I feel like this could potentially turn into something neat that we could simplify, but I can't see that immediately without taking the time to just sit down and slowly expand it. Plus, there's also a chance that we don't get something very clean. The only other thing I could do immediately right now is pull this r squared out of the square root as just an r, so there's that. R times the square root of alpha squared plus all this stuff to the fourth. But at the very least, what we do see from this is that your total acceleration is indeed a function of time and increases in magnitude as more and more time passes with this driver stepping on the gas pedal and applying a tangential acceleration. But yeah, I think that is all I've got for you for today. In terms of homework, I don't know if you really need it. If you stayed on top of your kinematics, you shouldn't be having much trouble with rotational kinematics stuff, but you can just look in the book for any problems. Let me go ahead and actually open our course plan and see what I recommended. Let's see, so chapter 9 and 10. I think chapter 9 was the one that had the rotational kinematics questions. Let me check. And again, if you don't have this book, it's linked at the top, very top, right over here. Anyway, chapter 9. No, chapter 10. So 10.1 and 10.2 is what you want to look at. Don't look past that just yet. Oh, I think I see why I listed rotational inertia earlier in my list, probably to match the book. Yeah, I'm not going to do that. So yeah, look at questions, both conceptual and practice problems, exercises, up to 10.2, up to section 10.2, and you should be good to go in terms of practice. Wow, a lot of conceptual questions. Okay, here are the exercises. Where did they start? There you go, the exercises start over here. Maybe it would help if I zoom in a little bit. So if we look at, it looks like you especially want to do the ones in section 10.2. Okay, there's not that many of them, but if you want to take a quick look through them and see, you know, just take a quick glance at them and go, oh, this one's easy, I know how to do this, skip. This one's easy, I know how to do it, skip. This one, I'm not so sure, let's work it out and see what happens. That's kind of the mentality you want to have. And of course, if you have your own textbook or other source of problems, feel free to use that as well. But really easy section for today, despite me kind of complicating it here and there due to some brain malfunctions and getting distracted with a bunch of YouTube videos that I want to recommend, apparently. But that's it for today. Next time we will talk about the topic of torque. We are going to look at it just from the perspective of how it changes our static equilibrium problems. And then after that, in the stream that follows, I want to introduce, actually, maybe in the next stream itself, maybe at the end of next stream, we'll do, let me think, how do I want to do this? So we'll introduce torque, we'll do static equilibrium problems, and then we won't do anything with it just yet, but maybe towards the end of next stream, we can at least introduce moment of inertia conceptually, just so that it's not completely foreign when we use the stream after that to start talking about the other place where torque is used, the other equation where torque is often used in this chapter. Well, I say the other equation as if there's only two. Torque is used in, let me think, 2, 3, 4 places. There's 4, I can think of 4 places off the top of my head, 4 equations that involve torque, 2 of which are the most commonly used: static equilibrium problems and angular acceleration problems. But We do sometimes see it used in problems involving energy and something that we will learn later called angular momentum. But yeah, that's the plan for the next couple of streams. I will probably stick with tomorrow for our next stream, but no promises on that. I might postpone it to Tuesday. If I do, I will probably be doing it earlier in the day when most people in my country will be at school. So I guess you'll have something to look forward to when you come back from school on Tuesday if I decide to postpone it. If not, then it'll be tomorrow. And actually, I'm gonna have to look because I might be needed somewhere tomorrow, but if not, I can probably get it done earlier in the day. We'll see. If you just, check and refresh the page every now and then to make sure that I haven't updated the scheduled time. If you really, really want to see it live, most people prefer to look at these lessons in post, which is perfectly fine. But for those who really want to know when they're going to be, I like to give that heads up. Anyway, that's enough from me. I'll see you next time, whether it's tomorrow or the day after or the week after, given how sporadic my schedule can be sometimes. Take care. Class dismissed. I'll see you in the next one.